So today we're going to be talking about IV equations within pharmacy. So that would be your IV flow rates and drip rates. In order to be able to do these equations, it's always good to know the ratios that you should end up with. So for flow rates, we're going to be looking for milliliters per hour. For drip rates, we want to end up with drops per minute. And in order to get our drip rates, we need to find something called our drop factor. So I'm going to write this a little to the side just so you know that it goes hand in hand with drip rates. And the drop factor will be in drops per milliliter. So what is a drop factor, you might ask? So a drop factor, basically, as you can see, it's drops per milliliter, so it's the size of the drop. Now you may be saying, we just learned about, drop sizes. So what we learned was 20 drops per 1 milliliter, and that's your standard size. So this would be what you would use for like eye drops or ear drops or whatsoever. But with IVs, sometimes we need to manipulate this size depending on if we're giving more or less of a dose. So our smaller drops, let's start off with that. So this tubing would be known as microdrip. And it gives a drop factor of 60. Then we have macro drips. And these give drop factors of 10, 15, or 20. And remember, drop factor is in drops per milliliter. So all these drop factors I'm giving you are in drops per milliliter. A lot of the times you will see drop factor, however, just listed as the number. I'm writing it down because that's how you will usually see it, but just know that it will be in drops per milliliter. Learning medical terminology, different prefixes and suffixes can change the meaning of a word. So micro, we learned, meant small, and macro meant large. So if we have 60 drops within 1 milliliter, if we can fit 60 of something into one thing, those things are going to be much smaller than if we can fit 10 of the same thing into 1 milliliter. So let's show this with an example. So let's just say we have a 500 milliliter bag to be infused starting at 11 a.m. And that is to be administered at a rate of 200 milliliters per hour. And we want to know at what time the treatment will be completed. It wants to know time, but not just the time that it will take to complete the treatment. It wants to know specifically at what time the treatment will be completed. So we know that we're going to have to add the time that we get to this 11 a.m. It does give us a flow rate, but we need to figure out what this flow rate will be for the size of our bag. So the size of our bag is 500 milliliters. So let's take the information we know and solve with it. So I'm going to use this right here, the flow rate given, as my given. So 200 milliliters per 1 hour. And we want to know how much time it will take with this 500 milliliters. So now I'm going to cross multiply because I'm using ratio proportion here. Divide both sides by 200 to isolate x, and we get 2.5 hours. But we're not done yet. Remember, it's not asking how long the infusion will take. It's asking what time it will be done at. So we need to add it on to this 11 a.m. now. So 11 a.m. plus 2.5 hours equals 1:30 p.m. Or if this is a hospital and we need to use 24-hour time, this would be 13:30. And I get that because to get 24-hour time, you take any time that's 12-hour afternoon and you add 12 to it to convert it to that 24-hour time. So if you add 12 to 1:30, then you get 13:30. And that's your answer. Now let's look at a problem dealing with IV drip rates. So for this example, I have a 1 liter IV bag that is to be administered at a drop factor of 60 over 8 hours. And we want to know what the drip rate will be. So in order to solve this problem, there are two different but pretty much the same equations that we will need to remember. And these all are based off of dimensional analysis. So let's start. So as I said, we're going to be using dimensional analysis, so the whole concept of needing to cancel units to get the units that you want. So remember, we are trying to find drip rate, which is drops per minute, milliliters per hour times drops per milliliter times 1 hour over 60 minutes equals drops per minute. So how this works, as I said, we want our units to cancel to then get drops per minute, or the drip rate. So here, milliliters, since they're diagonal units, they would cancel out, and we would be left with drops per hour. If we multiply that by hour per minute, these hours here would cancel, and we would be left with drops over minutes, which is what we want. If it's still difficult for you to memorize what to start with and how to keep going, an easy way to look at this would be, how can you memorize milliliters per hour? Well, milliliters per hour is the flow rate. How can you memorize drops per milliliter? Well, drops per milliliter is the drop factor. How can you memorize 1 hour in 60 minutes? Well, once you multiply these two, remember, you will get drops per hour, and you need to convert that to minutes. So this helps you convert hours to minutes. Now, if this is still confusing, the other way that you can simplify this same equation, so just simplifying dimensional analysis, would be to take your total volume in milliliters times your drop factor and then divided by the total minutes, which you would get by taking hours, the hours that are given, times 60 minutes. I'm going to take a different color highlighters just so I can show this. So this is basically a simplified version of the above because volume you get right here. Drop factor. Remember, this you can just put, like if the drop factor is 60, you can just fill in 60. For the dimensional analysis one, you would have to put 60 drops over milliliters, but this is where your drop factor is. The hours, converting hours and minutes, remember right here. So right here is where you get this part. So this is just a more simplified version of the above. Let's look at some examples with this. So right here, remember, we're starting with the flow rate. Now normally with the flow rate, you would want to make this in 1 hour, so you'd want to figure out how many milliliters are in 1 hour. When plugging in the flow rate for these types of problems, you can put it in as, for instance, right here, we can put it in as 8 hours. We don't have to convert it to that 1 hour. So I'm going to do just that. But first, I already see that there's something else we need to do. Right here, we're given 1 liter. And we're supposed to fill in for milliliters. So we need to convert this. So I'm going to use my metric conversion acronym. King Henry died by drinking chocolate milk. And liter is a base unit, so I'm going to start with my base, and I'm going to loop my decimal place all the way to milli, since we need to make milliliters. 1, 2, 3. I moved my decimal point 3 loops to the right. So if I take 1 liter, take my decimal point, 1, 2, 3. This is my new decimal point, and I need to put in zeros for my loops. So 1, 2, 3, 1,000 milliliters. I'm just going to make this 1,000 milliliters. Okay, so now we know that we can take 1,000 milliliters over 8 hours, and that is our flow rate. Times, here we're given a drop factor of 60. So 60 per 1 milliliter. Multiply that by the conversion to change hours to minutes, which is 1 hour over 60 minutes. And we're going to multiply across. This is dimensional analysis, so we multiply across, not cross multiply. So if we multiply across, we are left with 60,000 over 480, which then equals 125 GTTS per minute. It asks us to find the drip rate. The drip rate from before, we know, is drops per minute. We have drops per minute, so this is our answer. Now let's solve the same problem, but using the other equation. So remember, from the problem, our volume was 1,000 milliliters. We found that by converting that 1 liter to milliliters. So we have 1,000 milliliters. Our drop factor was 60. And we had 8 hours times 60 minutes. If you do this, you get 480. So once again, we have the same ratio we had when we were done multiplying for dimensional analysis. So we have that 60,000 over 480. And if you divide that, you get 125 drops per minute. So, same thing. Now, let's just say that we need to find the actual flow rate in 1 hour. So right here, as I said, we can solve using the flow rate in any amount of hours. But sometimes you might need to find it per 1 hour. So, what you would do for that is you would take the flow rate that you found here, 1,000 milliliters over 8 hours, and you would set that equal to 1 hour over, and we need to find the amount of milliliters. So 1,000 times 1 is 1,000. 8 times x is 8x. Divide both sides by 8, and you get 125 milliliters per hour. And that is your flow rate.